Unit 1 and 2 lecture outlined for 1045. I just want to let you know that this lecture outline does not replace Newton assignment. It does not replace the book. This is just to help you to understand the book and make it easier for you to do the Newton assignment, read the book, do as many problems as you can to feel comfortable taking the quiz and the exams. So I do have some sample problems. I do have some definitions, but not everything from the book is covered. But the ones that I found to be more either challenging or need like a sample problem, I added to this PowerPoint. Okay, in this example, we have there's a question asking you what is the density of the density of a lead if the cube of the lead has the edge length of 2 centimeters and the mass of 90.7 grams. Now, what's the first thing you want to know? What's the formula for density? The formula for density is mass over volume. Now, the unit for density is gram for solid compound, gram per cubic centimeter. Now, the information given, so you need the formula, which formula you're using. You want to know what is given and what is looking for. What's looking for is density. What's density? What's given for given is mass, which is 90.7 grams. The information for volume is given, but is not directly. They don't always give you direct information directly. Sometimes it's indirectly. So we don't have the volume, but we do have the dimensions. So the volume in this case is not given directly. So, but we do have 2.0 centimeter for each edge. So it would be the height times length times width. So you have to multiply the 2, and then you get the 3 times for the length times width times the depth, or the 3 dimensions, in order to get the volume, which gives you 8.0 cubic centimeter. Then you replace that into formula, is 90.7 gram over 8.0 cubic centimeter. Whatever number you find there is going to be the density. So 90.7 divided by 8.0. The answer is 11.3375 gram per cubic centimeter. Now, this is a calculated number. What should be your reported number? Your reported number should follow the significant figures. And I'm just going to correct myself, because if this is a 2.00, and this is 2.00, you have 3 significant figures here, 3 significant figures, and you keep the first 3 digits from the left side. So it's going to be 11.3 gram per cubic centimeter. So basically you have to round it up. You look at the first unwanted digit, which is 3 in this case, and since is less than 5, you drop, is less than 5 and is after decimal point. So you drop and you don't add anything. because if it's before decimal point, the story is different. And if it's greater than 5, you add 1 to the previous digit. So this is less than 5 and is after decimal place. So you don't have to do, you don't have to add to previous one. This is the final answer for density. Okay, next. Next is another example. And I wish the writing would go with the slide. How does it work? So I'm going to erase this to answer this question. The question is, a student drops a 3-kilogram block into a tank containing 100 milliliter of water. The block sinks to the bottom of the tank and the water level rises to 101.25. Now, that's the indirect measuring of volume for anything that is irregular shape solids. So we do have a block, we don't know the dimensions, or maybe it's not standard dimensions. We can't calculate by using mathematical formula. So we do by displacement. In a displacement, what is saying that you have a graduate cylinder and has it or containing a tank that has 100 liters. Okay, so let's say you have 100 liters of the water here, and when you drop the object in, it's going to displace and go to 101.25 liters. The difference here, the displacement would represent the volume for the object. So the volume is going to be 101.25 liters minus 100 liters, and the answer is going to be 1.25 liters. Now, in terms of decimal places, when you're adding or subtracting, you count the decimal places or not the significant figures. So if we have here 2 decimal places for each of the given numbers, the final answer can keep 2 decimal places. So we report this as the reported number for the volume. Now we are looking for density. Density is mass over the volume. So in order to calculate the density, you would say 3.00 kilogram over 1.25 liter, whatever that number is. The number is, use the calculator for that. 3 divided by 1.25, I could guess that is 2.4. So it's going to be 2.40 kilogram per liter. And that is the final answer. So C would be the correct answer. Now, the second part of the question is asking if the density was 1.5 kilogram per liter and you place in the tank, would it sink or would it float? What makes the object to sink or float is the density. If the density of the object is lower than the density of water, then it will float. If it's greater, it would sink. So what you need to know is that density for water is 1 gram per milliliter or is 1 kilogram per liter. So since density 1.5 kilogram per liter is greater than density of water, which is 1 kilogram per liter, then it's going to sink. So if it's a multiple choice questions, you choose your answer, but if it's a free response, you have to explain why would it sink or float. Next questions. Okay, for the next question, just erase these numbers again. Is asking you how many inches are in 232 millimeter. And the definition is given for you. 1 inch equals 2.54 centimeter. If you are using dimensional analysis, anytime you are using dimensional analysis, you are going to start with the given number. Okay, you're going to start with the 234, and that is a millimeter. You want to know what is your conversion factor that would change this to inches. Do we have a relationship between the inches and the millimeter as a given? No, we don't have it. We have the centimeter. So first we have to change the millimeter to centimeter. And by definition, 1 centimeter equals 10 millimeter. So I want to cancel millimeter. I want to change to decimeter or to centimeter. So centimeter has to be up 1 centimeter over 10 millimeter. So basically, as I said in class, you are going to take these two possible conversion factor, 1 centimeter over 10 millimeter, can extract that from this equation, or 10 millimeter over 1 centimeter. And then you choose one of these two options. Since you want to cancel the millimeter, you have to use A because you want to cancel the millimeter and you want to convert to centimeter. So that's not the final answer because we are looking for inches. Now, to find the inches or number of inches, it's 1 inch equals 2.54 centimeter. Now, again, we have two equations here. One equation, two possible conversion factors. And one is 1 inch just over 2.54 centimeter. The other one is 2.54 centimeter, 1 inch. Which one are we going to use? You want to cancel the centimeter, so we are using the one that centimeter is in denominator, and we can cancel it. 1 inch over 2.54 centimeter. Now, units that are canceled, centimeter with centimeter, and inches would be the last or wanted unit. That's what we are going to end up with. We want the inches. We have these numbers, so it's going to be basically 234 divided by 10 is going to be 23.4. So 23.4 divided by 2.54, and that is 9.21259. I'm not using all the digits. I'm using only allowed number of significant figures, and the allowed number of significant figures it's 3 in this case. And why is 3? Even though we have this 1 here, this is part of definition. We do not count. For determining the number of significant figures, we are looking at the given number only, which is the 232 millimeter. 3 significant figures, the final answer with 3 significant figures. Definitions, which is these two boxes here, or conversion factor based on the definitions, they have unlimited number of significant figures, and we don't have to worry about counting the significant figures for that. Okay, that's this example. Next. Wish we had a choice that it would raise in a touch. How many seconds are in 3 hours? And how many yards are in 3 meters? For 3 hours, we are going to start with the 3 hours. I'm going to change this to 3.00 hours. 3.00 hours. How many seconds? So it's easier to go from, if you remember 1 hour is 3,600 seconds, you can use that. If not, you can go to minutes and then to the hours. We want to cancel the hours, so it's going to be 1 hour equals 60 minutes. That's not the final unit that we want, but we know that we can cancel the hours at this point. You want to cancel also minutes and change that to seconds. So it's going to be 60 seconds over 1 minute. Minute would be also canceled. And you are going to do the multiplication. Is 3 times 3,600. 3 times 3,600. And that is 10 800. Okay, we started with 3 significant figures. We have 3 significant figures, so we don't have to do anything. That's just a comma, and that is the number of seconds. Question number 2, how many yards are in 3 meters? For yard to 3 meters, if you know direct conversions, that's what you use, is a shortcut, but it's not easy to remember. So what you start with the 3.0, and if you did remember, you can replace it. As long as you have the right conversions, it's okay. Okay. 3.0 meters. We want to go to yard. First, I'm going to go from meter to centimeter, from centimeter to inches, from inches to feet, from feet to yard. So multiple steps. Okay, unless you know what to, you know the conversion, like if you know the shortcuts, how many inches are in 1 meter? If you know that already, then you can use that. So if you know that there are 39.37 inches in 1 meter, you can use the conversion. You can use that shortcut. You can use that. If not, you could go to centimeter and then to inches. So to make the steps shorter, I'm just going to use this conversion at this point. But if you don't remember this, you can go from meter to centimeter is easy. There are 100 centimeter in 1 meter, and then 2.54 centimeter is 1 inch, and 12 inches 1 foot, and 3 feet is 1 yard. So I'm going to take this conversion now. I'm going to go to inches first. So I want to change to inches and cancel the meter. So 1 meter goes down because I want to cancel the meter, and 39.37 inches would go up in the conversion factor. I'm going from inches to feet. So it's going to be 1 foot over 12 inches. And from feet to yard, so it's going to be 1 yard to 3 feet. The final answer is going to be 1.09 yard. 1.09 yard. If we insist to have like two significant figures, then I have to change this to the two significant figures. Let me keep it as the two significant figures. So we practice rounding up here. It's here we have more than two significant figures, and you want to change the two significant figures, you have to keep the first two and drop the rest. The first digit that I'm dropping is greater than 5, so I add 1 to the previous digit, and that makes it 1.1 yard, and that would make it final answer. Okay. Next example is, this is going to be a long presentation, and the next example is asking what is the density of antifreeze in gram per milliliter if a 4-quart sample of the antifreeze weighs this many pounds. So because it's asking for gram per milliliter, we have to change the quart to milliliter first, and we have to change the mass to gram as well. Okay, so we have quart, 4.00 quart, and we want to change that to milliliter. So we change it to liter first. 1 quart is 3.78, so it's going to be 1 quart 3.78, or that's 1 gallon is 3.78. 4 quarts is going to be, I think 1 gallon, 1 quart is not 3.78. This is an error on someone's site. Okay, 4 quart is 1 gallon. So 1 quart, so 4 quart is going to be 3.78. 3.78 liters, and that is for 4 quarts or 1 gallon. And you want to change that to milliliter, is going to be 1,000 milliliter over 1 liter. So liter would cancel with liter, and quart would cancel with the quart. So this is going to be 3.78 times 10 to 3 milliliters. And you want to change the mass, 9.26 pound to gram, is going to be 1 pound. So every 1 pound is, LB is for pound, so this is supposed to be LB here, pound, and that is 453.6 grams. So we have to do this math first. 9.26 times 453.6, that equals 4,200. 4,200 grams. And we want to divide that by the milliliter. And that is going to be 1 point, so density is going to be 4,200.33 divided by 36 0.780, that's gram milliliter, and is 1.1 gram per milliliter, and that is the answer. So you want to make sure the units are matching. Okay. This question is asking, is a theory question, basically is asking which one is true, which of the following is true for, let me see if I can read the question, true about the homogeneous mixture, and select all that applies. The homogeneous mixture is a solution. So you need to know definition for homogeneous mixture. So that is correct. Homogeneous mixture is a solution. Homogeneous mixture can only be separated chemically. That is false, because by physical means, like by distillation, by you can separate. Also, homogeneous mixture is not uniform, and that is incorrect because solution is a homogeneous mixture. A homogeneous mixture is not a pure substance. Is a mixture, so it's not a pure substance. So A and D would be the correct choices here. What about heterogeneous mixture? For heterogeneous mixture is going to be, when you talk about heterogeneous mixture, they maintain their identity, and in the mixture, component of the mixture maintain their identity. And you can see that all compounds, they are not uniform throughout the mixture, and they can be separated by like filtration, by decanting, by separated funnel. So it's more visible for heterogeneous mixture. Now, this question is asking which of the are physical property. So physical property, those are the property that it can be observed, it can be seen by senses, or it can be measured. So chemical property, those are properties that it has to do with the chemical composition of the compound, like ability to go through chemical reaction. That is going to be a chemical property. In this case, color is physical property. Flammability and toxicity would be chemical property. So the choice is A. For next question, which one is intensive property and which one is extensive property? What is intensive property? Means that intensive property does not depend on the size of the sample. If you look at mass, the more object you have, the greater the size of the object you have, the mass is going to be greater. The weight, which is the gravitational force, also is going to be greater. So mass and weight and volume, those are extensive property, but intensive property would be color. Other examples for intensive property is like boiling point, melting point. It doesn't matter you have a drop of water, the freezing point is going to be 0 degrees Celsius. And if you have a tank of water, freezing point is going to be 0 degrees Celsius. Boiling point the same. As long as the sample is pure, boiling point is going to be 100 degrees Celsius for pure water, regardless of the sample size. So when you are measuring level of the liquid in a cylinder-shaped equipment, you are looking for the lowest point of the curve, which is called meniscus. So it's the bottom of the meniscus, okay? And if that level does not follow an exact number, then what you need to do is that with a graduate cylinder, you have to mentally subdivide the distance between the the number that is below the level and the number that is above the level. So between 21 and 22 in this case, how do we know this two are 21 and 22? Because you have 20 and then 25, and between 25 you have 5 spaces. So each space, it represents 1. So this level now is between 21 and 22. If you subdivide that to the mark into like 10th of the millimeters, this case, I'm sorry, 10th of the milliliters, then you count like about how much or how many point of milliliter is going to be higher than the 21. So you would say like this number about 21.6. If it's closer to the 21, you would say 21.4 or 0.3. And when you give this number, 2 and 1, those are certain digits, because you could see this line. You could see the line of 21, and definitely the level of the liquid is higher than 21. Definitely is lower than 22. So it's between 21 and 22. So we are sure that 21 is correct. But 6 is an estimated number, because if I could see this as a 0.6 and someone else would see as a 0.5, then we are not going to argue. We're just going to say, okay, I'm estimating this as a 0.6, and then I just leave that as an estimated digit. And if you estimate as a 0.5, it's okay. There's nothing wrong, but you cannot, for the certain digit, we should all agree, because the measuring device would show those numbers. Just when you're counting significant figures, it needs a lot of practices, but I want to make sure that the only part that is about like the zeros, like all non-zero digits are significant. Everyone knows that. The zeros requires a little bit of thinking. Now, if you have a captive zero, that means zero between 2 non-zero digits, that is going to be significant. But if you have a trailing zero, it depends if you see the decimal place or you don't see a decimal place. Now, if I have a decimal place, which is right here, the decimal place is visible, the trailing zero is going to be significant. So this is significant. The captive zero is always significant. Okay. Leading zeros are never significant. So these are not significant. The zeros before the first non-zero digit, these are not significant. So not significant, not significant. This is significant, that's significant, because I can see the decimal place. For the trailing zero, if you don't see, like in this case, there is no decimal place, you only have 3 sig fig here. So it's going to be 3 significant figures here, because the trailing zero, when the decimal point is not visible, is not significant. So here you have 4 significant figures. Of course, they're all, and in this case, you have 3 significant figures, because the trailing zero is trailing zero, but since you have the decimal, you can see the decimal point, then the trailing zero becomes significant. Another example that we have, it's very similar to what we have here, so don't worry about that one. Subatomic particles, atomic number, atomic number of protons, number of neutrons, and the electrons. Those are subatomic particles. And using the subatomic particles, we can find out what is atomic number, what is mass number for any element. So number of protons is going to be, number of proton is the atomic number, okay? Atomic number, or Z, that's number of protons. Mass number For atomic mass, this is the number of protons plus number of neutrons. So since we have the mass number total of the two and the atomic number just number of protons, whenever you want to find the number of neutrons, you would subtract the mass number minus the atomic number, or atomic number from the mass number, in order to get the number of neutrons. Atomic mass unit is a definition, and that is the 1/12 of the mass of carbon-12. It is defined as 1 AMU, atomic mass unit. Every element in the atom of every element in the periodic table is compared to the carbon-12. So if you have an atom of something like magnesium that weighs 2 times as atom of carbon, it would be 24 AMU, or something is half of it is going to be 6 AMU. So 1/12 of the carbon atom 12 is going to be 1 unit, atomic mass unit, because the mass of the atom is very small, and that's why they had to use very, very small unit for that as well. So atomic mass of a single atom, it's equal to the mass number of that atom. Okay. But when you look at the periodic table, in the periodic table, you have some decimal places. So how do we get decimal places? Because when we say the mass number is number of protons and number of neutrons, and those are all whole number, and if you add like 2 whole number, you should not get decimal place. How do you get decimal place in the periodic table? In periodic table, what is recorded is the average mass. For the average mass, it's the fractional abundance of the atom times isotopic mass. So if you have element that has 2 or 3 different isotopes, and they do have different popularity, different abundance in nature, then we have to do the calculation. So let me see if I have example here that makes it easier. So we have, in this example, close that, you could see it, sample of the gas of neon. It shows that you have 91% of neon 20 and 0.47% of neon 21, and 7.69% of neon 22. So we have 3 of them. So when you are summing up, we have to have 3 separate parentheses, and each parenthesis would give the fractional abundance. That means that is going to give me the decimal place for that, or decimal representation of that number in the percentage value. So when you say fractional abundance, that means 91% is going to change to a divide by 100. So you get 0.9184% of the mass of neon 20, and the mass of neon 20 is given here. Okay. In the second parenthesis, you have the mass of the neon 21, which is a 20.99. This number is given to you. The percentage was 0.47%. So you divide that by 100, it was going to be 0.0047. That is the percentage or fractional abundance. And then you have the third parenthesis is for the third isotope. If the element had only 2 isotopes, this would have changed to only 2 parentheses, and each parenthesis would show you what you should include the exact mass for that isotope and the fractional abundance of that isotope, which is the percent given divided by 100. So that gives you the fractional abundance of that. When you add them all up, you come up with a weighted average, just like calculating the GPA. If you have 4 class, you take 4 classes, you get 3A and 1B, your GPA is going to be closer to A. But if out of the 4 classes, you have 3B and 1A, your GPA is going to be closer to B. Same thing here. Now, the majority of neon has the mass of 19.99, which is close to neon 20. So the average or weighted average mass for neon is closer to 20, not close to 22 or 21. So when you are calculating the final answer, it should fall between the mass, the lowest mass of the isotope and the highest mass of the isotope. The highest mass of isotope was 21.99, and then the lowest mass of isotope was 19.99. So final answer should fall between these two numbers. Your final answer should be closer to the one with the greatest abundance or greatest fractional abundance. And since 1999 is greater in the abundance, the final answer should be closer to 20 and not to 22. Other definitions that you need, because you're studying chemistry, so you have to know about the chemical formulas. There are 2 definitions that I want to talk about here. One is the molecular formula, the other one is empirical formula. So what is the molecular formula? Is a representation of a molecule, uses chemical symbol. So molecule is a combination of different number of the atoms. So when you say benzene has, okay, when you say benzene has the chemical formula of C6H6, this is the molecular formula for benzene. That's based on that formula, I could say the type of the element or the type of the atoms in that molecule are carbon and hydrogen. I also have the actual ratio of carbon to hydrogen. There are 6 carbon and 6 hydrogen per molecule of benzene. So it gives those are the type of the information that you can get. How many different elements or atoms are per molecule, and then how many of each. If the actual number is given, that is called molecular formula. Now, what happens if you get the lowest ratio? If you get the lowest ratio, like you have the C1H1 here or a CH, that would give you the empirical formula. The empirical formula is the lowest whole number ratio. So it shows what type of elements you have or what type of atoms you have in that. And also it shows the simplest whole number ratio. It does not give you the actual number. Sometimes empirical formula and molecular formula are the same, okay? Like the TiO2, empirical formula is TiO2, molecular formula also is TiO2. But other times, when you are looking at a compound like this, C2H4, I think it's for acetic acid, C2H4O2, the actual number is 2:2 ratio, but the lowest ratio, if you divide all of them by 2, is going to be 1:1. So when you have the 1:1, this is empirical formula, but when you have the actual number, it's called molecular formula. I also want to mention about the diatomic molecules. With the diatomic molecules, you have the hydrogen, oxygen, nitrogen, chlorine, bromine, and iodine. 1, 2, 3, 4, 5, 6, 7. There are 7 of them in the periodic table that they always appear as diatomic. Like when you have later on, when you write chemical reaction, you cannot write O. It has to be like O2 because that's how it appears in nature. But when it combines with another element to form a compound, then it depends on the compound. So for like H2O, you need 1 oxygen per molecule, so you use 1. For hydrogen peroxide, you need two oxygen per molecule, so you use H2O2. So you cannot write O2 just because it's diatomic, because that's going to change the nature of the compound. This is edible compound. This is a toxic compound. It's like strongly oxidizing molecule. So we cannot drink this, but we can, you know, this is like, of course, water. Edible compound. So empirical formula, molecular formula, diatomic molecules. That's the summary of this slide. And time-consuming raising, it's okay. I can deal with it until I learn how to get. Okay. Based on Dalton's atomic theory, just another definition that we want to know, the atom is the smallest unit of the element. Atom is the smallest unit of the element. Okay, smallest unit for a compound is molecule. Smallest unit for element is atom. When you have a combination of metal, non-metal, like if you have NaCl, is a metal, non-metal, the smallest unit for that is known as formula unit. Sometimes they also say molecule, but it's wrong. It's supposed to be formula unit if it's ionic compound. But if it's a molecular compound, like in benzene, C6H6, the smallest unit is molecule. When you have a bunch of molecules in one container, and it's just pure, is everything of that same, is called a compound. But if you have a bunch of just aluminum in like a piece of aluminum, that is known as the element. So element is made of one type of atom only. Compound is made of different types of the atoms. Okay. The law for definite and multiple proportions. In the definite proportion and multiple proportion, this law, it says if you get a sample, let's say you get a sample of the compound with the carbon dioxide sample, if you get from, or water, any sample, you get from a lake, purify it. And then you get from another, you get from Davy, you get from Fort Lauderdale, you get from anywhere. When you do the percent composition, the ratio of mass of oxygen to hydrogen for water is going to be the same. So the ratio of mass of oxygen to hydrogen for water, or mass of carbon to hydrogen in carbon dioxide, is going to be the same. It doesn't matter, as long as it's the same for any given compound, is the same compound. So still is the same compound. That's what is basically means. So we compare the ratio of the sample of for each sample, you compare the ratio of carbon to oxygen. If that ratio becomes the same mass ratio, then the two compounds are the same. If, like in this case, the mass ratio is not the same, then these two are different compounds. So that's what basically is saying. The definite proportion is for the same compound. Each compound has a fixed proportion of the mass of one element to another element. So if the two samples, they have different mass ratio, these are two different compounds. Compound A is not the same as compound B. Now, if you find a compound C that is made of carbon and oxygen only, and then you find the ratio, and the final ratio for compound C was 0.750 carbon over 1 gram of oxygen, then you would say A equals C. But A is not same, sample A is not same as sample B. Okay, in a periodic table, elements are classified. They are in groups and periods or row. Okay, and each of these groups, they do have different name, which you are going to, some of these group names, you have to know the name, and you can refer that to book or other PowerPoint presentation. And not sure if everything is covered in this, but group 1A, 2A, you have 3A, 4A, 5, 6, 7, and 8A. These groups, 2 on this side, and those two, those are group A elements. They are also known as representative elements. The representative elements, then you have this group here. These are known as the transition metals. And then we have 2 rows of the elements under the periodic table. These are known as inner transition metals. Now, what type of information? For now, it's not about the classification, it's about what type of information you get from the periodic table. So if you look at the periodic table, there are 2 numbers in each box, 1 symbol and 2 numbers in each box. The numbers that I see in the first box for hydrogen is 1 and 1, or 1 and 1.00. Okay. For carbon, I see 6, a number 6, and then I have, if I round it up, it's like 12. For hydrogen, I see 1 and 1. Except for hydrogen, for everything else, these numbers are different. So the smaller number is known as atomic number, or Z. The greater number, regardless if it's written up or down, this is a mass number. And for the mass number, symbol A is used. The difference is number of protons. Got it. Okay. If the element, so again, for those that you have, for those elements that you have like at decimal places, I already said like 35.45 for chlorine. What you have those, that means that that compound, that element had multiple isotopes, and then we took the average mass, and based on the average mass, now we have the decimal place. If the element has no other isotope, it's just one isotope, one sample, you're not going to get the decimal place. These are some of the samples of the elements that we have. If there is an isotope, you see the symbol is the same. Okay, the symbol is the same. Number of the proton is going to be the same, which is the atomic number. Atomic number is the same as number of protons. So number of protons is the same for these 2 hydrogen. Number of neutron is different. So definition for isotope becomes, these are the atoms of the same element, because element did not change. We have H and H. They have same number of protons, or same atomic number, or same number of protons, but different number of neutrons. If you have like 3 neutrons, then you have hydrogen 3. If you have 1 neutron, it's going to be hydrogen 2. If you have 0 neutron, it's going to be hydrogen 1. Hydrogen 1 is the only element in periodic table that has no neutrons. Okay. Helium. You have, how many isotopes we have for helium? We have 2 isotopes. That is the helium-3 and helium-4. Helium-3 has 1 neutron. Helium-4 has 2 neutrons. And for helium, the number of protons or the atomic number is going to be the same. What about number of electrons? If your element is neutral, number of electrons is always going to be equal to number of protons. Because all elements are neutral, number of proton equals to number of electrons. But number of neutrons, it could be different than the protons, and it can also be different from one isotope to another isotope of the same element. So if you look at these examples, you can see that they are different in the number of neutrons. We have 3 isotopes for carbon, carbon 12, 13, and 14. Now, if you want to find the subatomic particles for W182, that's tungsten 182. Now, what are subatomic particles? Basically, what's the number of protons, electrons, and neutrons? In order to find that, we have to go to periodic table and look for W. And when we look for W, we go to the periodic table and look for W. And when you look for the W, you should look for the symbol W right here. And with the symbol for W, you see that atomic number is 74 because we have a 74 and then 182 here. So we know that a smaller number is the atomic number. So this is going to be the 74 is going to be the atomic number. So we have the atomic number for that. So if you have atomic number of proton is going to be 74. So number of proton is 74. Number of electrons is going to be 74. Why is 74? Because these two numbers must be the same because we don't see any charge here. If there is no charge, that means number of proton and electrons are the same. Proton have positive charge. Electron, they have negative charge. Neutron has no charge, is 0 charge. So we don't consider the number of neutrons when you are looking at the charge, number of electrons and protons only. How do you calculate number of neutrons? Number of neutrons is going to be the mass number minus the atomic number. So we find the number of neutrons here. So this is the number of neutron 108 for this element. So in order to find subatomic particles, especially for number of neutrons, you need the mass number. Why they don't give the number of protons or the atomic number in this question? Because that is a assigned number. Because if you change that to 17, then you cannot say W. 17 would always be chlorine. If you change that to 8, that would always be oxygen. So atomic number is the symbol or the number, assigned number to each element. If you change the atomic number, the symbol is going to change. In a normal chemical reaction, the atomic number or number of proton never changes. When you have a compound reacting with another compound, with another element, number of electrons might change, might be transferred, might gain or lose electron, but number of protons do not change. Protons and neutrons, they are in the nucleus of the atom. There is another name for them, and that name is do not touch them. Okay, we don't touch the protons, number of protons or number of neutrons in a chemical reaction, unless you're dealing with nuclear reactions, which we are not. Okay. Subatomic particles, we've been talking about subatomic particles, but let's see, we have the table here. Electrons, where they are. The nucleus of the atom has protons and neutrons. The protons and neutrons, okay? They are in the nucleus of the atom. So positive charge is in the nucleus of the atom. Electrons, they are orbiting around the nucleus in a specific energy level. So electrons are around the nucleus. That's where the location is. The charge for the in coulombs is a very small charge, but the unit charge assigned is a -1. So electron has a -1 charge. Mass of the electron is very small also in gram, and they just ignore the mass of the electron. They say electron has no mass. Proton has a 1+ charge. It's inside the nucleus and has 1 unit mass. So mass of proton is going to be 1, about 1. So we are just using 1. For electron, we use 0. For proton, we use 1. And for neutron also, we use 1. Neutron doesn't have a charge. The charge for neutron is 0. The mass for neutron is 1 AMU. Okay. Mass of the atom is condensed inside the nucleus because only protons and neutrons, they have the mass. Electrons, no mass and no contribution. The size of the nucleus is very small. Basically, an atom is like basically an empty space, and only electrons are orbiting. Okay, so if you kind of compare this, the diameter of the atom, and this is the diameter roughly for the nucleus, it's 10,000 times smaller, or 100,000 times, sorry, 100,000 times smaller. So it's very, very small. It's like you have like a baseball field, and you do have a baseball in the center. So that's the nucleus, and this is the baseball field, is the mass of the area that for the atom. So what I told you about, like slightly about the Bohr model, and I said that they are in the electrons are in different energy level. And what we know is that from the Bohr's model is that energy level is going to be, the energy level is going to be lower for the energy levels that they are, the energy is going to be lower for the levels that they are closer to the nucleus. So for the atom to spend time in level 1 is going to require less energy. If the atom is in level 2, it's going to have more energy. If it's in level 3, it's going to have even more energy. Now, if the electron wants to go, if I said atom, it was a mistake, it's electron, I'm talking about electron. If the electron wants to go from level 2 to level 3, that's like jumping, it needs electron, it needs energy, and that energy can be given as a photon, like light or heat, and then electron can go to higher level. Now, if the electron jumps back from higher level to lower level, that energy is going to be released. So if it's going from level 3 to level 1, energy is going to be released. Even more energy is going to be released comparing to if it's going from level 3 to level 2. So this is going to be more energy being released. So that's basically the Bohr model. The formula to calculate how much energy is going to be released is right here. This is the formula. It's known as the Rydberg equation. Okay, with the Rydberg equation, what's the final, where electron is going to be landing? What's the initial energy level? And also the RH. This is the Rydberg constant, is a constant value, and that number can be memorized or will be given to you, is calculated based on the Planck's constant, and you can find this number is a given number, so it can be calculated, or you just in the problem will be given to you. That is a Rydberg constant. But to calculate how much energy is going to be released or absorbed, you are using this equation. Or this equation is the same, but the order is different. If you are using the minus sign here, it would be final and then initial. If you are using a plus sign for here, for R, is going to be initial minus the 1 over the final squared. N represents which level is going to move up or down. Okay. The question here is asking, an electron jumps from second to third level energy of the atom. What can we assume about this atom? The atom is emitted a photon that was equal to the energy gap between level 2 and 3. Okay. Would the energy be emitted or absorbed? Because if it's going from level 2 to level 3, it needs energy, so it cannot be, cannot be true, right? This atom emitted a photon that was less than the energy gap. That is also incorrect, because first of all, it's going to be equal to the energy, the gap of the energy. Second, is absorbed and not emitted. This atom absorbs a photon because if it's in level 2, has less energy. If it wants to go to level 3, has more energy or needs more energy. The difference in energy needs to be absorbed, and C would be the correct answer. So when you find the energy from the Rydberg equation, when you find that energy, you can plug in that energy value into this equation, and then you can find the wavelength, because sometimes question is asking for energy only, other times is asking for the wavelength. So if you find the energy from the Rydberg equation and you are looking for the wavelength, you are using the Planck's constant, you are using the value for C, which is the speed of the light, and you're finding the value for E. If it's not given to you, only the levels are given for the atom, then you are using the Rydberg equation to find the value for E. Okay. Just an example here is a solved problem. As I didn't want to use the calculator, the presentation is already long. I didn't want to make it longer. So in this equation, the question is, what's the energy in joules that is needed for hydrogen transition of electron from level 4 to level 6? It doesn't say is the energy is being absorbed or is being released. But when you find the amount of the energy, if the energy that is found is positive, that means that energy has been absorbed and is understood, because if it's going from orbit 4 to orbit 6, energy must be absorbed. So the Rydberg equation, if the positive negative value is used here, this is the final minus the initial here. So Ni to the power square and F square, and we have that negative value here. And then the delta E that is calculated is a positive value. That means this energy has been absorbed. Now, if you want to find the value for lambda or the wavelength for that energy, you are using the Planck's constant. This is the Planck's constant, 6.62 times 10 to 34 joule times second. And then the speed of the light, 3 times 10 to 8 meter per second. And then the energy is calculated energy from the Rydberg equation. So you want to find that. So when you find the energy, what else you can do with that energy? First of all, you can find the energy that is, if it's absorbed or emitted. So if it's positive, that means has been absorbed. If it's negative value for the energy found, or the delta E, that means the energy has been released. You can find the value for lambda, which is the wavelength of the photon that's being emitted. And you can also find the value for frequency, because frequency times wavelength, that gives the speed of the light. And if you want to find the frequency, you just divide the speed of the light by the wavelength to find the frequency. Electron configuration. I'm going to stop here.